Okay. Today I'm going to talk about Lyman-alpha cross-section in more detail. I'm going to present a classical derivation of the Lorentzian cross-section, and then we'll talk about the cross-section in quantum physics as well. So before doing so, I just wanted to clarify one thing. Yesterday, this was based on a question I got after the lecture. I mentioned yesterday how the collisional excitation rate of the Lyman-alpha transition depends extremely sensitively on temperature, right? So you saw these few orders of magnitude rise in the collisional excitation rate coefficient over, very narrow range in temperatures. And someone was asking, like, is this, and then I basically said that, at some point at 2 × 10⁴ Kelvin, you have ionized away most of your hydrogen. So in principle, the collisional excitation rate of neutral hydrogen atoms goes down again, right? So your cooling rate, your Lyman-alpha cooling rate rises very sharply above 10⁴ Kelvin, and at some point it reaches a maximum and turns over. And someone was asking about, like, if this explains the behavior of the cooling curve, and that's, of course, that's exactly what is behind this kind of figure, right? So here I'm showing, say, the cooling rate of a primordial gas as a function of gas temperature. And here you see exactly the same behavior, right? Where the cooling rate of primordial gas, so only molecular gas levels, etc. And then you sort of reach a maximum when hydrogen ionizes away, and you start going down again, and you have repetitive behavior, because then you start cooling through collisional excitation of singly ionized helium. But this is, this is the same thing. Okay, sorry. So today I'll talk about the cross-section, right? So what I will talk about specifically is, what cross-section is, differential cross-section and phase function. These are very key concepts in radiative transfer, as we will talk about this afternoon. I'll talk about the Lorentzian profile. I'll derive it actually in the classical sense, and I'll compare it to the proper calculation in quantum physics, which is actually quite remarkable. I'll talk about the Voigt profile, which is a simple extension of the Lorentzian profile, and I mean, we've heard this in X's talk. I'll go a little bit in more detail on this as well. And once we know this, then I think we are set up to understand why we need to actually do radiative transfer of Lyman-alpha through the interstellar medium. Right, so, okay, so this is how I will start my presentation. So in a classical sense, you have radiation as an electromagnetic wave, right? So that electromagnetic wave is shown here. So you have your radiation coming in this direction. The radiation has an electric component which is oscillating, and a magnetic component which is oscillating in this direction. Right, and let's say this electromagnetic wave is incident on a free electron. So what I'm going to do first is I'm going to discuss the interaction of an electromagnetic wave with a free electron. Right, and this gives us an expression for what is known as the Thomson cross-section, Thomson scattering cross-section. And this allows us to introduce concepts like the differential cross-section, phase function, etc. And the interesting thing is that many of these concepts are very useful when looking at Lyman-alpha radiative transfer and Lyman-alpha scattering, right? So that's why I'm doing it. And it also gives us with a basic formalism that you can extend to a bound electron, right? So after this, we're going to do exactly the same analysis, but then have the electron be bound to a proton, right? And then things change a little bit, not much. But then it turns out the Lorentzian profile is going to drop out automatically, which is very nice. Okay, but first free electron, right? So what happens is you have your free electron sitting here, you have this electromagnetic wave coming in this direction. Now what happens is that the electron, when it sees this electric field associated with this wave, it starts oscillating along the direction of the electric field, right? It's being accelerated. Now what I will write down, because I realized that this is when I actually memorize it myself much better once I've written things down a few times. But in any case, the acceleration of the electron is just given by, if you have the electric field, you multiply by the charge of the electron, you divide by its mass, you get the acceleration, right? And I've put absolute symbols around these quantities. So the acceleration is just related to the amplitude of the electric field of the wave. That's it, right? But I already mentioned in the very first lecture that if you have an accelerated charge, right? If you have an accelerated charge, it starts radiating, right? So, and I mentioned this in the first lecture that in the classical sense, atoms are not stable. The electron spirals in, and you basically have no atom left after like 10 to the minus 10 seconds, right? So the total power that you radiate, that this an accelerated charge radiates, is given by the Larmor formula. And I'm just going to write that down because I'm going to use that. I'm going to use that repeatedly today. Right, so if we write down the total power, I'm going to call this P out. That's simply given by 2 over 3 times the charge of your particle squared, right, times the acceleration squared over c cubed. Right, this is the famous Larmor formula. Now what we care about often is we care about time averages, right? So if we just take the time average radiated power, then we can just take the time average of this particular quantity, right? As the wave is coming in, the acceleration changes as a function of time, and we're just going to consider, if you average over a whole sequence of wave fronts, this is what we're going to care about in the end. So we're going to take the time average of the acceleration of the electron. Right, and this formula is going to be key to the whole discussion, basically. Okay, so I've written that down. Good. I won't have to erase it. Now the other thing we know, so the cross-section is simply defined as, when we think about this incoming radiation field, you have this incoming electromagnetic wave. The cross-section simply defines as the total power that is re-radiated by this accelerated charge, the total power, so energy per unit time, over the total flux that was coming in the beginning, right? So that would be the total power per unit area. Right? If you take the ratio of these two, so total power would be flux per unit time, and the denominator we have flux per unit time per unit area. So the units you get is an area, right? And so we basically have a scattering probability that has units of an area, so that's basically a cross-section, right? So this is the very definition of cross-section, basically. Now, in the classical sense, we know what the total flux or the total flux in an electromagnetic wave is, right? In a time average sense. It's given by, if we describe the electric component of the electromagnetic wave, say by E naught times sine omega t, then the total flux in that electromagnetic wave is just given by this expression here, right? And that's in standard E&M books. So now I'm actually already very far, right? I've already specified, I know what P out is, right? That's given by the Larmor formula. See, it works on the blackboard as well, my pointer. So we have an expression for P out, we have an expression for F in, right? So in principle, you can almost calculate the cross-section automatically, right? So, well, let me just do it then, before I, right? So you can in principle, so I already wrote down that the acceleration of the electron is simply given by, the absolute value is simply given by the electric field, right? Times the charge of the electron over the mass of the electron, right? This is the acceleration. Right, and we're interested in the time average of this, right? So, we're interested in the square of this quantity. So, since I'm taking the square, I might as well drop the absolute signs, right? So I'm just going to drop the absolute signs here. For simplicity, I should not. So the square of this is just square of this, of course. So we're going to be interested in this, this, this. Now, I'm interested in time averages, and this electric field is just E naught times sine of omega t, right? So I'm interested in the time average of sine squared omega t, and that's just half. So if I want to say time average of this particular quantity is just 1/2 E naught, right, the amplitude of the electric field, times Q squared over ME. Now I can combine these two equations and I'll just get that substituting equals 2/3 Q squared over C cubed. Right, substituting this here, I have 1/2, so I have, let's just get rid of this 2 here, I have a 1. Right? E naught squared Q squared over ME squared. So I have my P out, I have my F in, right? And then you get a ratio, you can write down the ratio of the two, you get an expression for the Thomson cross-section. Right? So look, I have a Q squared here, Q to the 4th here. So I have 1/3, right, Q to the 4th, E naught squared over ME squared, C cubed, over F in, right? So I have a C E naught squared, and my 8 pi goes up here. Right? And the nice thing here, of course, is that the amplitude of the electric field falls out, which is good because you don't want this property that is associated with a single electron to be related to the properties of the incoming wave, right? So this nicely falls out. Right? We have a C to the 4th here, we have a Q, well, let me just collect some terms. I have 8 pi over 3, right? And I have some factors here, Q to the 4th, ME squared, C to the 4th. And it turns out that this quantity here is exactly the classical electron radius squared. It's kind of nice because this expression tells you that you basically, RE would be the classical size of the electron, so it basically tells you that the probability for scattering with units of area is just the classical size of the electron, almost basically the area of the classical area of an electron if you want to define such a thing. Right? There's an extra factor, weird factor of 8/3 there compared to like a true geometric cross-section, but that's just that's just the way it is. Right, so this is the Thomson cross-section, and it's a very important concept in radiative transfer, I think. Yeah. Now the thing is, as you can already see here, right, the cross-section has this P out over here. In general, we do not think that this radiated power P out is isotropic across the sky. So you have this accelerated electron, it's oscillating in a certain direction, and the re-radiated emission is not isotropic. And let me just draw that as well. I'm going to use the blackboard again to do this. I was debating whether I should use the whiteboard. What do you prefer, black or white? Black. I didn't quite understand you, so I would like to do an online. No, I'll just do the whiteboard. Okay, I'm going to keep this. So I'm going to consider again, suppose that you have your incoming wave is propagating in the blackboard, right? It's coming along this direction in the blackboard. My electron is sitting right here. This is the electron. Right, and I'm going to define, so we're going to call this direction the propagation direction of the incoming radiation. So this is a unit vector k in. Right? So the propagation direction of the outgoing vector is given by k out. And again, I'm going to say that this lies exactly in the board. So this scattering plane is the blackboard, basically. Right, now I know that if K in lies inside the board, right, it lies nicely here, we know that the electric and magnetic vectors are lying in a plane perpendicular to K, right, and perpendicular to this board. So my electric vector is going to be somewhere in a plane perpendicular to this blackboard. Now imagine that for simplicity, for example, that my electric vector is also in the plane of the board. It's pointing in this direction. I'm going to denote this direction with E, unit vector E, subscript E, just to denote the direction of the electric field. Now you can imagine that if you are an observer looking at this electron is moving like this, right, up and down like this. Now I'm an observer sitting in the direction given by K out. Suppose I were to sit all the way here, I would not see the oscillation of the electron at all, right? It would just be sitting still for me. Right, so it turns out that then you can say, okay, since this observer is not seeing the electron oscillate, right, there is no acceleration associated with the electron, there is no associated power emitted in this direction associated with the electron, right? So that's a way to see it. You can look at it. But on the other hand, if the observer were to sit here, it would see the full acceleration of the electron, and it would see the full power of the full emitted power given by this equation, right? So this gives you some insight into why there is some directional dependence to the re-radiated power by this accelerated electron, right? And right, so here I basically repeat the geometry that I've just drawn on the blackboard with slightly more detail. Right, so what I've drawn here in the diagram here is it's a bit more general. I've sort of relaxed the assumption that this electric vector is actually lying in the board as well. But the argument is exactly the same, right? You can pick your electric vector going this direction, as long as it was perpendicular to the incoming direction. That's all that matters, right? Now, we can just define a new angle, psi, which indicates the angle between the electric vector and the outgoing direction. Right? So if this is the angle, then we can say that this angle is defined by the dot product of K out and E in, or EE basically. Right? This is the definition of this angle. Right. So you can also see then that as I was just saying, like if psi is 0, you basically see no acceleration. If psi is at 90 degrees, you see the full acceleration, right? So the apparent acceleration, and let's just call this A tilde, or A whatever, like I don't know what this is called, I think it's tilde, would just be the true acceleration of the electron times sine of psi, right? So that captures exactly what I was just saying. So the re-radiated power is since the re-radiated power is proportional to the acceleration squared, the re-radiated power is proportional to sine squared of psi, right? So it gives a very strong angular dependence to the re-radiated power. So this already tells you that for Thomson scattering, the re-radiated power is highly anisotropic, right? Now in practice, there's one more step we have to take, because in practice we do not care about the directionality of the re-radiated power with respect to the incoming electron vector. We care about the directionality of the re-radiated emission with respect to the incoming radiation, right? So now suppose you just had a beam of radiation, that all your radiation was coming in from this particular site. We would like to know what the re-radiated radiation is of scattered radiation basically, averaged over all possible electric vectors, right? If the radiation is unpolarized, we should take the average over all possible orientation of the electric vector. Now, and I do this in the lecture notes, I go through this analysis explicitly, and then you can show that once you go through the analysis, you average over all electric vectors, you basically find that the re-radiated power goes as 1 plus cosine theta squared. And theta would now be the angle between the incoming and outgoing direction, right? So this would be your angle theta. So just to stress that this 1 plus cosine theta squared averages over all possible electric vectors of all possible orientations. So this is a very famous result, right? that the scattering amplitude goes as 1 plus cosine theta squared. This is also known as, well, Thomson scattering or dipole scattering, right? And so one way to write this is as follows, right? You can say that the re-radiated power has some angular dependence to it, right? And this is often expressed in this function called p theta. And it's a bit confusing that I'm using both p here and here, but that's, you know, that's just, I think, historically a bit unfortunate. That's just the way it is. Right? But this has nothing to do with power. This is known as the phase function. So this fully quantifies how the re-radiated, the angular dependence of the re-radiated emission. And then this phase function is really, yeah, it's important. If you normalize it to this, right? So if you define mu as cosine theta, if you define this this function to be 1, which it should be because, you know, radiation is, well, basically you want the total amount of radiation should be equal to the total as given by the Thomson formula, right? Thomson cross-section. If you normalize it properly, you get this prefactor of 3 over 4 here, right? So P mu is 3 over 4 times 1 plus mu squared. So that's exactly what the 1 plus mu squared is just what I was describing earlier. Now to contrast this with the case of isotropic scattering, that would just be 1/2, right? This would be the case for when radiation would be scattered completely isotropically in all directions with equal probability. Now, why am I showing that? We will get to this in more detail later, but the interesting thing is for Lyman-alpha, it turns out to be a superposition of both. Right, so Lyman-alpha turns out to be, if you look at Lyman-alpha resonance scattering, it's, you can describe it as sort of a superposition of 1/3 dipole scattering plus 2/3 isotropic scattering. Right, so it's a bit strange. But one way to see it is why this is the case is again related to what I was talking about in my first lecture, right? That Lyman-alpha scattering excites this 2p level of atomic hydrogen. The 2p level of atomic hydrogen has these very weird double-lobed kind of, right, okay, that's a good question actually, has this very weird double-peaked, double-lobed well, wave function basically. So this is from my first lecture, right? So 2p was characterized by these really weird, well, this double-lobed wave functions. So you can imagine that if you know, we'll get to that in a second in more detail, but you can imagine that if you were not have if you have a quantum system like a hydrogen atom in quantum physics, your incoming wave comes in, it excites the hydrogen atom. Right? The electron is not really free to oscillate nicely as I was showing you before along the electric vector. Instead, the electron is just going into this wave function that expands into these double lobes, right? But these double lobes, the electron can be anywhere in here, right? It can oscillate anywhere within, well, as far as is allowed by the wave function. Right? So it turns out that you know, there is some, you know, so you can imagine that the hydrogen atom has some memory of the direction of the incoming photon. It is just a bit smeared out by this strange shape of the atomic wave function, right? I guess to make my point a bit more clear, if the shape of the wave function in the 2p level were symmetric like the 2s level, right? Then you could basically say, like, once the atom goes into the excited state, it has no memory anymore of the direction or the electric vector of the incoming vector photon at all, right? So then, in this particular state, you're equally likely to emit in any kind of rate, in any direction. But that's not the case for the 2p level. The 2p level is not spherically symmetric. The 2p level has some memory of the incoming radiation. Right? So that's why Lyman-alpha isn't quite isotropic. Scattering isn't quite isotropic, and it isn't quite dipole either. It's somewhere in the middle. And we'll get to it when I talk about polarization. The reality is actually even crazier. It turns out that the precise level of what the precise weight is of dipole scattering versus isotropic scattering depends on frequency a little bit, and in a very strange way. Okay.
Excuse me.
Yeah.
With this argument, I understand why you have that anisotropic term, but I don't quite understand why you have also the isotropic contribution.
Well, okay. That's a good question. what I was saying is, I think the anisotropic term, the dipole term, this particular term was derived, incoming wave has an electric vector, and you basically oscillate perfectly along the electric vector. That gave me the dipole term. What I'm saying is that for Lyman-alpha, you go into your excited state. The atom is not, the electron is now not perfectly oscillating along the electric vector. It's instead moving in an orbital which has, doesn't have an infinitely thin width, right? Like the orbital has like it has this weird shape, right? So it's almost like the electron is moving in this way, but it's also moving a little bit in this way, it's moving in this way, it's in this way, right? So it's sort of smearing out this nice dipole pattern. Maybe that's a better way. Maybe I should have said it like that. Like the main point is that Lyman-alpha scattering is not quite isotropic and not quite dipole. It's in between. But to come back to the classical picture for a bound system, right? So now I'm going to do the same analysis, just like before, but now the electron is not free to oscillate in whatever way it likes, because it's bound by this proton, right? And we're going to assume it's bound by this proton, and it has a natural frequency going around the proton. Right? So the idea is that it's a nicely bound system. We're going to ignore for the moment that in classical physics this is unstable. It's actually even fair, because the interaction that we're talking about takes place over such a short time scale that over the duration of the time scale, scattering time scale, this is pretty stable, right? Even though the atom is collapsing over 10 to the minus 10 seconds, this process would take place over a time scale of many orders of magnitude smaller than this. So I think that's fine. Right. So I'm not going to go. There's no time for that. But in the lecture notes, I'll go in a bit more detail about this. But you can write down the equation of motion for this particular system, right? You have your electron that is orbiting in a proton with a natural frequency omega naught. There's an incoming electromagnetic radiation that has a frequency omega, which is different. And it turns out that this system you can describe by what is known as a forced damped harmonic oscillator. Right? And so that's basically the equation that describes it. It's very similar to what we described earlier. Previously we had exactly the same terms, we just didn't have this one and we didn't have this one. Right? This would just be due to the natural motion of the atom around the proton, and this damping term here actually takes into account that if the system were left alone, the electron would spiral inward over a very short time scale. So it's actually there. Right? So it turns out that if you have this kind of differential equation, right, then you should go look for solutions of this particular form. Right? So xt. So x would now just be if we think about it, you have your proton, you have your electron going up and down, just like before. X would just be the amplitude of the separation of the electron from the proton when viewed from the side, right? So it's very similar as what we discussed before. X would be the amplitude, and this exponential term would just describe the oscillation around equilibrium. Right? So we're going to try solutions of this particular form, right? And I'm going to just do one step here. Right, so the only thing you have to calculate now is, once your solution takes on this form, xt equals x times e to the power I omega t. Your first derivative would just be x times I omega times exponential e omega t. Right, that would be your first derivative, and your second derivative, you pick up another factor of I omega, right? So you get x I omega squared exp I omega t. And now you can plug in these solutions into your equation. And one thing you can see, right? You have your x double dot, like all these terms here, all of them have this x e to the I omega t, right, by construction. So these nicely cancel out, they're gone, so you don't have to write these up. Right, so I won't, but I will write up what you get once you substituted everything in. Is it still, I can actually erase this part here. I won't erase Larmor's formula because I think that would be offensive. I won't erase Voigt either. That would be even more offensive. Okay. Right, so just let me, I'll just substitute these expressions into the differential equation. We're going to drop the exp I omega t because they are everywhere, right? And just write down the result. Right, so what we get is, right, so we're just going to have x times, right? X is everywhere as well, except on the right-hand side, so that's what I'm going to keep it. Right, from the x double dot term, I have this I omega squared, so that's just minus omega squared. Right, because I squared is minus 1. We have gamma x dot, so we have one term plus gamma first derivative, so that gives me I omega. And then we have the first term, or the omega squared naught term. And this just equals q m times E naught. And I'm going to solve for the amplitude x, so I can bring everything over to the other side. Right? So let me just write this down explicitly. So we have q E naught over m. And in the lecture notes we'll have most of whatever intermediate steps were there. These are in the lecture notes, right? And right, plus. So this will be the amplitude, basically, of the fluctuation, of the oscillation. And the reason I'm writing this up explicitly is that I want to make one more simplification. Right? I'm going to work, generally speaking, we work at frequencies pretty close to the Lyman-alpha resonance. Right? So omega is going to be very close to omega naught. Right? So in that case, it turns out it's convenient to approximate omega naught squared minus omega squared. You can write as omega naught minus omega times omega naught plus omega. Right? Now if we work in the limit where omega is very close to omega naught, we can say, well, these two are roughly equal, so we're going to just write it as follows, right? And I wanted to do this because once you do this, then things start to look like after a few steps, things start to look like the Lorentzian profile. Right, so once you do that, now suddenly you have in your, right, well, so that's what I've actually, never mind. This is actually what I derived here, right? So now I get an expression for x, right? This is what I've given on the board. Now this is, the reason for doing this is because we would like to compute this re-radiated power, which was proportional to the, which was proportional to the acceleration squared, right? And we know how to compute the acceleration. The acceleration is just the second time derivative of x. Right, so we have this x factor times e to the I omega t. We're plugging it all in, and what you get, right, we're just going to plug in, going to use the famous precious Larmor formula, plug it into the expression for the cross-section, and what you get after some manipulation is this. Right? It's kind of miraculous. So, and you can sort of see the origin of all these terms, right? Like you have your omega minus omega naught squared. That comes from your omega minus omega naught that is in the denominator here. You have your gamma squared over 4, which actually comes from your gamma that is in the denominator here. So you can sort of trace back the origin of all these terms. What is remarkable, this is not quite Lorentzian profile that we've seen before. It is. It turns out that there's this extra. There's this extra omega over omega to the 4, not to the 4th term in here, which is actually pretty cool. Right, so let me and I'll come back to that in a second. So this is a plot of this cross-section that you compute, right? And it turns out, well, I'll say that in a second. Just plot the cross-section as a function of frequency offset, and this is exactly what X was showing us before. It's like extremely sharply peaked on the Lyman-alpha, on the resonance of the line, right? Or the natural frequency associated with this damped oscillator. But what is amazing about this is, this is the Lorentzian profile that we've seen many times before. And I remember X was nicely explained that the finite width of the cross-section, it's not a delta function because of quantum fuzziness associated with the first excited state, right? It's interesting that in this classical picture you get exactly this kind of profile, the exact same profile, but it's not due to the fuzziness with any excited state, but it just reflects that, this electron has a natural frequency while going around the proton. So if you irradiate the system with radiation with a frequency very close to that natural frequency, the system responds very strongly to it, right? And this is a classical example of a resonance. If you look up resonance, what it means I don't know the exact words, I haven't written it down, but I think it's an unusually strong response of a system in response to an external stimulus or whatever, trigger, right? So it comes in very naturally in a classical sense as well. But what is exciting about this is that you have this omega to the omega over omega naught to the fourth power term in there. And that's known as Rayleigh scattering, right? This is why the sky is blue, for example. It means that the cross-section is higher if you go to higher frequencies, right? So, for example, Rayleigh scattering describes scattering in the limit where the size of the radiation or the wavelength of radiation is much larger than the size of the scattering particle, and that's the case, for example, for Lyman-alpha, right? And the Lyman-alpha frequency wavelength is much longer than the typical size of a hydrogen atom, well, definitely than the hydrogen atom in the ground state. Right, so this is Rayleigh scattering. So it describes why the sky is blue. And this is actually a nice picture that comes with the wiki page of Rayleigh scattering, right? I'm not sure exactly what this is, but it's really nice. This thing is being irradiated with it's optical radiation, and you can sort of see that the radiation that propagates through and is not scattered leaves a red reflection here, right? And the blue radiation is, of course, scattered. And it's exactly because of this lambda to the minus fourth dependence of the scattering cross-section, or the omega to the fourth dependence of the scattering cross-section. So that also comes out of the classical derivation. And what is interesting is that this term doesn't just gives us a Lorentzian profile, it actually agrees perfectly what you would get quantum mechanically. So this expression here is one you would find in Peebles' 93 famous textbook. Right, it's the same. If we identify this gamma term with the Einstein coefficient of the transition, and in the lecture notes I actually show you that the only difference between this and this is actually the oscillator strength that X mentioned. That's the only difference. And that's a quantum mechanical thing. So that's completely understandable that we didn't have that. Right? This term, the origin of that, I don't quite understand. The Peebles calculation is a quantum mechanical derivation, but it assumes a two-level atom. Right? You get this extra term, which generally speaking is negligible anyway. Right, so we get basically the perfect answer. Now, okay, in the final minutes, I just want to show the behavior of the cross-section in the far wing of the lines, and this is where quantum mechanics comes in. Never mind the y-axis at the moment. I think that's not that important. What is shown here is the cross-section in the extreme wings of the line profile. Right, and extreme in the sense that this is wavelength over Lyman-alpha wavelength, right? So this is 2 would correspond to Lyman-alpha cross-section at 2400 angstrom. This would be the Lyman-alpha cross-section at 3600 angstroms and at 5000 angstroms, right? So this is, in many purposes, it's not really practical, but just to show you that, that there are some interesting corrections to these cross-sections. So 2-level would be this dotted line here. That would basically be the cross-section that I derived classically as well. Right? And the solid line would be the full quantum mechanical calculation. So it does agree like close, quite nicely, right? And this is the Lorentzian, Lorentzian is right here. Just to note that, so the simple calculation that we did that had this Rayleigh scattering term in here is actually closer to the true answer than the real Lorentzian profile that we heard about. It's kind of just as an interesting thing. What I think is what surprised me most when I saw this equation, so this was from a recent paper by Mortlock, a review article that appeared a few months ago, in which it comes from a paper in preparation by Mortlock and Hirata. They provide an expression for the cross-section, which is given here. The one thing that surprised me about this equation is that you actually, when you evaluate the Lyman-alpha cross-section at these very long wavelengths, you get contributions from photoionization, right? So a low-energy 5,000 angstrom photon photoionizing the hydrogen atom, right? That actually gives you a contribution to the Lyman-alpha cross-section in the wings. And that to me was, just bizarre. I mean, I think it's just another application of quantum tunneling, right? The photon doesn't have nowhere nearly enough energy to actually do this, but it makes a noticeable correction to the cross-section. And I don't have a complete list of references here, but it is remarkable that this shape of the cross-section is still, there are still papers being published on this. And just to go the final things, the Voigt cross-section. So in practice, the Lorentzian profile is not quite what is relevant, because the Lorentzian profile or the Lorentzian cross-section, or whatever I was just showing you before, is for a single atom. Okay? And in gases, atoms move, right? So you look at a particular parcel of gas, and atoms have different motions, so the resonance of each atom is actually slightly different, and that sort of washes out this very sharp feature in the cross-section, if you average over many atoms. So this, if you want to account for this effect, you have to integrate, or you have to average over basically the velocity distribution of your atoms, right? So the cross-section for Lyman-alpha absorption is generally temperature dependent because this velocity distribution is temperature dependent, right? And then you have to sort of convolve this Lorentzian cross-section or whatever functional form you choose for your cross-section with this velocity distribution of atoms, and this gives you the Voigt cross-section, right, or the full cross-section. Technically speaking, the Voigt cross-section is when you convolve the Lorentzian with the velocity distribution, but as we know, the Lorentzian is only an approximation, right? And this is just to show you the velocity offset, the cross-section as a function of velocity offset from line center on the y-axis, right? So 10 kilometers per second, 100, 1,000. This is for gas at 10 to the 4 Kelvin. But I'm showing a number of cross-sections, so this will be a Gaussian, this will be the Lorentzian just the Lorentzian, this straight line, right? And the Voigt would be overplotted here, right? So it's actually, as X already showed as well, is that in the far wings of the line, you recover the Voigt cross-section goes to the Lorentzian cross-section perfectly, right? So whatever corrections you want to make to the cross-section through quantum mechanics, these will also enter here in the Voigt or whatever, the total cross-section. And I'm going to call it Voigt profile anyway. Right. And I think one thing to note is that the peak of this cross-section is about 10 to the minus 14 centimeters squared. Right? And just for comparison, this is 11 orders of magnitude larger than the Thomson scattering cross-section. Right? So just, it's remarkable if you think about it, because whether the electron was bound or not makes 11 orders of magnitude in the probability that it can actually scatter incoming radiation at this particular frequency, right? So, it's a really nice example of a resonance again. So I'm done actually. So at 10 to the minus 14, with this kind of cross-section, for the typical H1 column densities that we see in galaxies, and this is H1 observations of galaxies, you have column densities of 10 to the 19, 10 to the 20, 10 to the 21. That means that if you multiply the cross-section by the column density, you get an optical depth. The optical depth or the opacity of the ISM to Lyman-alpha photons is of order million or 100 million, right? So it's tremendous. So that's why, of course, we need to consider the Lyman-alpha transfer of the photons. Right? And I'm going to talk about the first aspects of that radiative transfer in the next lecture. So that's it for today.